Okay, we're going to do a little kinetics experiment. I'm going to just take some blue food dye and I'm going to pop it into this, which that's got some water. So this just got water in it. This is our control. All right, just blue food dye and water. Over here, there's a mixture of hydrogen peroxide and some base that's a catalyst. Remember, we put a catalyst over the arrow. And it turns out that the dye, the blue dye, reacts with hydrogen peroxide in the presence of base catalysts to form colorless products. And so as this reaction proceeds, here we go, we're going to start it right now, in it goes. As this reaction proceeds, we would probably imagine to see that this blue dye on the left-hand side should fade over time, whereas of course there's no peroxide or base on the right-hand side. And so, this is going to remain fairly colored. So why are we doing this? Well, I'm doing this to tell you a way that we can often determine the order of a reaction with respect to a particular reactant by monitoring the amount of, in this case, the blue dye with time. So, for example, if we were going to monitor this particular reaction as it proceeds, we'd probably want to do a graph of the concentration of the blue dye versus time, like this. And you can already see it's fading a little bit. Maybe you can't, but I can. It does look like it's fading just a bit. I'm going to pop these over here to the side to let them go as we're talking. So there's a couple ways that this could actually happen. Sometimes when we do this particular reaction, we see the color fade in a straight line about like this. And, because we can see the color changing, we can measure, its concentration by its how deeply blue the color is. Sometimes we see it tail off like this, and other times we see it tail off quite rapidly like this. The concentration of the dye versus time, we see it drop really rapidly, much more rapidly than in the other case. So, we could imagine taking some quantitative data as to how blue this solution is over here, which of course is fading. And as we monitor the concentration of this dye versus time, it can give us clues into the order of the reaction, with respect to the dye. So by monitoring the concentration of a particular reactant with time, you can get information about the order of the reaction with respect to that particular thing that you're monitoring. So how does this work? Well, again, remember I told you we were only going to need to worry about zero, first, and second order processes. So I'm going to give you what each of these look like. So in the first case, if we have the dye concentration decaying in time in a linear fashion, so it's dropping in a straight line fashion, what you get is an equation that looks like this. The concentration of the dye at some time t later on in the experiment. So this, in this case, we'd be looking at this, I don't know, maybe 2-3 minutes later. So it'd be at time 2 or 3 minutes. This concentration here is going to be the initial concentration, or what we started at, minus kT. So let me talk about what each of these means, just so you know. This means the concentration of dye sometime later than when you started it. In this case, it would be sometime later after I added the drop. This would be the concentration of dye initially, which would be, close to this concentration, minus the rate constant K for the reaction times T, which is indeed time. And this would be the case for a zeroth order process. If the reaction rate does not depend on the concentration of the dye, it's just going to keep decaying at the same rate. And we don't know what it is for this particular case because I'm not taking any quantitative data. If you want to see that, I have another video where you can look at how to do this. Okay, what about first order? What about a first order process? What's that look like? Well, in this case, the first order decay looks like this. So this would be the concentration of the dye versus time. If we were monitoring this and it was first order, we would get an equation that looked like this. The concentration of the dye at some time t later on, after we added the drop, after we started the reaction, would be equal to the concentration of the dye initially, so we put a little zero down here to indicate right when I first started the reaction, times this number e to the negative kt. So this is in the exponent of this number e. You should know how to use that on your calculator. This is the rate constant for the reaction, and once again, this is your time. So this is the equation that's going to describe how first order decay works. And then finally, for a second order process, it's going to look like this. Let's see. This is going to drop off really quickly. Dye versus time. Woo, it's really going to drop quick, but it's still kind of curvy like this. Now I'm going to give you an equation here that's not found in your book, but it works. It definitely works. So this might be something that you want to use. In a second order process, the concentration of the dye at some time t later on is going to be equal to a fraction that looks like this. The concentration of the dye initially, like similar to what it was at the start, over 1 plus k, the rate constant, times t, time, times the concentration of the dye initially, like that. So here are our three equations that we can use to monitor or figure out what's the expected concentration of the blue dye in this at the time that we're at now, I don't know, about 5 to 7 minutes in, after I've added the drop. What's the expected concentration of the dye? If we know the initial concentration, we know the rate constant, and we know how long the reaction's been going. And it's going to be different for zeroth order, first order, or second order, and these are going to be the various equations that will describe the concentration of that dye at later times on during the experiment. Now, what we often do, however, is when we monitor, like if I was going to collect some quantitative data on the concentration of this dye with time, I could then analyze that data and figure out what's the order of the reaction with respect to this dye. And the way we do that is we do what's called, we linearize all three of these equations. And well, what does that mean? We just turn them into a form in which we can plot them and get a line. So let me show you how that works. We're going to do zero order first. So zero order. And what's nice about zero order is the linearized form of this equation is just that equation. It's the same thing. So the linearized form of the zero order equation is the concentration of our dye at some time t is the concentration of our dye initially minus kt. Now why is this a line? Well, here's why. I'm going to make this equal to y. So the concentration of dye at some time t, we're going to make that equal to y. The concentration of the dye initially, we're going to make this b. The intercept, right? Y equals mx plus b is where we're going. If we want to linearize something, we want to get it into the form y equals mx plus b. That's what we want. We're going to make the slope m negative k, and we're going to make x time. So let's see. This becomes b. This becomes plus, because it's a negative k, mx. There we go. Y equals mx plus b if I make these substitutions. And so what that means is if I take a plot of y, which is the concentration of the dye at some time t, so if I do that, and I plot that versus x. That's what we always do, you know, we plot y versus x. That's going to be versus time. I should expect to get, if it's zero order, I should expect to get a straight line because we've linearized the equation. I should get a straight line with a slope that's going to be equal to, so the slope of this line should be equal to the opposite of the rate constant. And the y-intercept is just going to be the concentration of the dye initially. And what's nice about this is we can check to make sure that, you know, we're doing the right thing here mathematically. The units of the rate constant in this analysis should be the units of the y-axis, which would be molarity, right? This is concentration, so this is units of molarity, divided by the units of the x-axis. We'll just call this seconds. So, right, the slope units should be the y-axis units divided by the x-axis units, in which case it's going to be molar per second. And if you go back and check, indeed, these are the units for a zero order process. Now let's just check out what our cups are doing here. I mean, this is almost gone. That reaction is it's almost done. Okay, let's do the linearization for a first order process. So you might remember that the first order equation was the concentration of the dye at some time t is the concentration of the dye initially times e to the negative kt. Well, if this equation is linearized, it's going to look like this. The natural log of the concentration of the dye at some time t is going to be equal to the natural log of the initial concentration of the dye minus kt. So the natural log is the inverse function of e to the power of x. So it works like this. The natural log of e to the x is x. If they're inverse functions, if I take e to the x, I get that value. I take the natural log of it. Those cancel. Or I could write e to the power of the natural log of x is x. They're inverse functions. And that's why as we linearize the equation, you go from e to the power of to natural log. Anyway, we got to get this equation in the form y equals mx plus b. So to do that, we make the substitution. We're going to make the natural log of the dye at time t. We're going to make that y. We're going to stick this on the y-axis. And we're going to make the natural log of the dye concentration initially. We're going to make that equal to the intercept. So this is going to be our b value. And we're going to, once again, we're going to make the opposite of the rate constant. We're going to make that equal to our slope. And once again, we're going to make time equal to x. So just like we did in the last case, we're going to put some form of the dye concentration, some mathematical form of the dye concentration versus time. If we look for first order, this is first order, right? Sorry if I didn't write that down. I didn't write that down. So for this first order process, our y, our mathematical form of the dye concentration, is the natural log of the dye concentration. So what we'll do here is we plot the natural log of the dye concentration at time t versus t. That's our x. This is our y, this is our x. And if we do that, you know, the normal here was what it normally looked like. This would be the dye concentration versus time. Normally, it looks like this, right? It's got this curvy form. Well, if it is indeed, if these data do follow first order decay, if we take, for example, the natural log of this value and plot it here, and we take the natural log of this value, wherever it is, and we plot it here, and we take the natural log of this value and we plot it, if it's first order, we're going to get a straight line. If it's zero order, we won't get this straight line. If it's second order, we won't get this straight line. But if it's first order, if we take these data and take natural logs of all these, you know, these y values here, all of these y values, and we plot them in this particular form, we're going to get a straight line. And if we see that, we say, ah, this is a first order decay of our blue dye. And if we do indeed see this, we know that our slope is equal to, so the slope in this case is going to be equal to the opposite value of the rate constant. And, of course, our intercept is going to be the natural log of our initial dye concentration. And if we want the units of our slope, right, that's going to be the units of the y-axis divided by the units of the x-axis. And the way it works is anytime you take the natural log of something, it should have no units. So we actually have, so my units are going to be the y-axis units divided by the x-axis units, because that's my slope. There's my slope units. My y-axis units is unitless, so I'm going to stick a 1 up there. And we're going to divide by the x-axis units, which would be seconds. So the units of my rate constant for a first order process will be second to the minus 1, which matches what we learned previously. So to recap where we're at, for a zero order process, if you plot the dye concentration versus time, you'll see a straight line. You have, aha, it's zero order. There's nothing else I need to do. If you plot the dye concentration versus time and you get a curvy line, well, then we gotta figure out if it's first or second order. The first thing we do is we check if it's first order. If it's first order, we take the natural log of all these values, we plot those versus time, and if we get our straight line, we know that that's going to be first order, and we can find the rate constant from the slope of the line. It's pretty nice. Well, what about the case where it is second order? You know, it could be this curvy line doesn't give us a straight line here. And in that case, we got to test for second order. So let's go to the second order case. Here we go. So second order, mathematical analysis, graphical linear analysis. All right. Our non-linearized equation is the concentration of dye at some time t. That's going to be equal to the initial dye concentration over 1 plus the rate constant times the time times the initial concentration. If we linearize this equation, it looks like this. It looks a little goofy. 1 divided by the concentration of the dye concentration at some time t. That's going to be equal to 1 divided by the initial dye concentration plus KT. And if you're good at algebra, you can go from here to here pretty quickly. Same is true over here. I'm not going to show you how that's done, but if you know your natural logs and all that, you can go from this equation to this equation in the first order case. And like, come on, man, that's not a line. How does that make a line? Well, let's make the following substitutions. If we make 1 divided by the dye concentration at some time t, we're going to make that y. So this becomes y. And then we're going to make 1 divided by the initial dye concentration. We're going to make that b, our intercept. And in this case, we got a positive sign, so I don't have to worry about the negative. Our slope, that's going to be the rate constant. And once again, time is going to be x. And if I do that, that becomes b plus mx. There it is, y equals mx plus b. So in this case, the mathematical form of the dye concentration we plot on the y-axis is 1 divided by the dye concentration. So again, we're going to take our original data, which is the dye concentration, versus time. That's gonna look very curved in a second order process. And what I then do to linearize it, what I would do is instead of taking, this dye concentration, I take 1 divided by the dye concentration. And to just show you how that looks, let's say we start at a dye concentration of 1 molar. Well, what's 1 divided by 1? That's 1, so we're going to start right here, okay? These are different scales. And then let's say right about here, it's down to 0.5 molar. So at this point, right here, we're down to 0.5 molar. Well, what's 1 divided by 0.5? Hey, that's 2. So at this point, we've moved up to 2. All right, so we'll say this was at time 1 second or something like that. All right, so here's 1 second. And then all the way down here, we'll say this is at 10 seconds. Yeah. All the way down here at 10 seconds, we're down to 0.1 molar. So way out here at 10 seconds, well, that's 0.1. What's 1 divided by 0.1? That's 10. That's going to be way up here. That's the way that's done. That's the way you do the transformation. I show it in this case and not the other case because this one's a little easier to see. And if we get a straight line through those points, we're going to pretend that's a straight line, okay? I had to eyeball it a bit. But if we get a straight line through these points, then we know it's second order. And the slope of this line is going to be equal to the rate constant. And the units of that, well, let's see. If the units of this are molar, the units of 1 over the dye concentration should be molar to the negative 1. And this would be time in seconds. And so the units of my slope units, should be the units of my y-axis, which is molar to the minus 1, divided by the units of the x-axis, which are seconds. So my slope units in a second order process should be molar to the negative 1 times second to the negative 1, which we already know to be the case. We learned that in a previous lecture. And here, my initial point here, right, the very first point right here, we know that is 1 divided by the initial dye concentration. We know that because we took it here. So that is linearization and graphical analysis of doing an experiment and monitoring the dye concentration over time, and how you can use those data to determine the order of the reaction with respect to the dye, with respect to the thing that you monitored. And just to sort of make a general overall recap of what we learned, it's going to be very useful for you to know these 3 equations. It'd be very useful in your, in the problems that you do, to know how to calculate the concentration of the dye expected at some time after you started the reaction, given a rate constant, and of course the time later on when you need to calculate the dye concentration. Like, you start the reaction in certain conditions and you want to figure out, well, what's it going to be here? Well, this is an equation you use to that. If it's a first order equation, you would use, a first order decay, you would use this equation to figure out, okay, my dye concentration started here, where's it going to be 4 hours later? Well, you can use this equation to figure it out, and you can also use this equation to figure out the expected concentration that occurs during a second order decay process. Where is it going to be at time t out here? What's the concentration going to be way out here after a certain time later, given initial conditions? The other thing that we need to know is these plots that we do to test for 0, first, and second order. In the 0 order case, you plot the concentration of the compound. I'm just going to call it A, whatever its concentration is versus time. And if you get a straight line heading down, it's 0 order. If you plot the natural log of your concentration versus time, and you get a straight line going down, it's first order. And if you plot 1 divided by the concentration of the thing you're looking at versus time, and you get a straight line going up, that's second order. And what's nice is the slopes of these lines. So the slope of this line is the opposite of the rate constant. The slope of this line is the opposite of the rate constant. And the slope of this line is equal to the rate constant. And so these are diagnostic tests. If you've collected the data, these are diagnostic tests to see if your reaction is 0, first, or second order with respect to the thing that you're monitoring. And in a subsequent video, we're gonna start to do some problems that allow us to see how to do this.